So specifically for a CSTR reactor, another equation that I can also plot on this representation of X versus temperature is my mole balance, just like what I've done for the irreversible reactions in the lecture slides part 1 for this theme. So here is now the mole balance represented for different masses of catalyst in my CSTR reactor. So for a reversible reaction, and you can go and plot the mole balance to make sure that you agree with this, I actually have this maximum possible and then it decreases. The mole balance for an irreversible reaction, if you want to remind yourselves, will go to X is equal to 1 using that shape, and it won't have this U-turn because of the equilibrium reaction. So this is not what's going to happen in my reactor. Remember, the reactor still has only one operating point. It operates at a specific rate, specific conversion, and where it operates still depends on where the energy balance intersects with that specific mole balance for that reactor size. And also given on the previous theme, and please go and revise, make sure that you can draw the rate graphs as asked in the previous theme slides for the different lines. So on this figure, just to remind you, it's a representation of iso rates. So if I want a rate of 500 moles per kilogram per second, and I am at let's say a temperature of 130 degrees Celsius, what must X be in order to achieve that same rate? So lots of iso rates on this figure, and you were asked to show how the rate will change for the different lines given on this graph. This is the adiabatic energy balance. We already plotted that for you on the previous slide. This is for isothermal conditions. If I keep the temperature the same, but I increase conversion, so decrease the reactant concentration, what will happen to my rate? Make sure you can plot that, and make sure that you can show that for each specific concentration, for each specific conversion, there is an optimum in the rate. So if I keep my composition the same and I vary the temperature, there is a temperature where my rate will be at a maximum. And it's a good idea to target a CSTR to operate, if I want a specific conversion, to operate at that maximum rate. So in order to, if I want a very high rate, what's often done industrially is instead of immediately jumping to that, even if I operate at that maximum rate point there for my 80% conversion, is to rather say start with a stepwise conversion, operate at the maximum rate there adiabatically, then cool it down adiabatically in a series reactor, cool it down adiabatically until you achieve your final conversion. Please revise the touch that describe this behavior to make sure that you understand the concepts. So for irreversible reactions, a very similar effect for the exothermic reaction is observed. Just shown here for an exothermic reaction is the slope or the shape of the energy balance, the modified mole balance for a CSTR. But if we just consider the rate for an exothermic adiabatically operated, regardless of the reactor type, once again, for each X, I will see a decrease in my reactant concentration and therefore a decrease in rate. However, for the exothermic reaction, I am going to see an increase in temperature with X. So the Arrhenius dependence of my K value. I don't have the reverse reaction that plays a role in this case. So I will once again observe an increase in the rate initially until it reaches a maximum value where the concentration effects start to dominate. But my rate will only go to 0 when X is equal to 1. So I will only obtain the 0 rate. I will once again see a maximum in the rate because I have an increase in temperature, increase in K value. And once again, the shape of this graph will depend on the relative value of my activation energy and my heat of reaction.